500 million light-years across, a structure hangs in space so vast that the Milky Way, its neighbouring galaxies, and thousands of others besides are only threads within it, all drifting toward a single gravitational low point that none of them will ever fully reach. For decades, astronomers thought they had already measured this structure and gave it a name, the Virgo Supercluster. That name is still used today, but the thing it names turned out to be far smaller than the structure it sits inside. What follows traces how far our galactic neighbourhood actually reaches, moving outward from one bound galaxy group to a crowded cluster to a supercluster and beyond, ending at a 500 million light-year basin of galaxies discovered only in 2014. Along the way, it asks a harder question too, what it even means for something in the universe to have a size, when its true edges are drawn by motion rather than by matter. Stars in the Milky Way orbit a shared centre the way water swirls around a drain, only far more slowly. The Sun takes about 230 million years to complete one full circuit, a length of time so long that the last time it passed this point in its orbit, dinosaurs had not yet appeared on Earth. Seen from far outside, the galaxy would look like a flattened spiral, several 100 billion stars arranged along sweeping arms of gas and dust, with a dense bar of older stars running through the middle. From inside it, on a planet a little more than halfway out from the centre, it is easy to mistake the Milky Way for the whole of everything. It is not even close. Step back far enough, and the Milky Way shrinks to a single point of light travelling alongside a small crowd of others. That crowd is called the local group, a loose gathering of galaxies bound together by their own gravity, spanning roughly 10 million light-years from end to end. A light-year is simply a unit of distance. The distance light covers in 1 year, about 9.5 trillion kilometres, and it is the only unit that keeps the numbers in astronomy from becoming unreadable strings of zeros. At 10 million light-years across, the local group is not large as cosmic structures go, but it is a real physical association, not just a region of sky. Two large spiral galaxies dominate it. The Milky Way is one. The other is Andromeda, similar in size, sitting about 2.5 million light-years away, close enough that on a dark night it is visible to the naked eye as a faint smudge, the most distant object most people will ever see without help from a telescope. A third, smaller spiral called Triangulum orbits nearby. The rest of the local group, close to 80 members by the latest counts, are dwarf galaxies. Small, faint collections of a few million to a few 100 million stars, many discovered only in the past few decades as surveys pushed deeper into the dark gaps between the bright galaxies. Most orbit the Milky Way or Andromeda, the way moons orbit a planet. Andromeda and the Milky Way are not simply neighbours. They are closing the distance between them at roughly 110 kilometres every second, pulled together by their mutual gravity, and current models predict that in about 4.5 billion years the two will begin to merge into a single, larger galaxy. It took astronomers a long time to even establish that Andromeda was a separate galaxy at all, rather than a nearby cloud of gas inside the Milky Way. That question was settled in the 1920s, when astronomer Edwin Hubble identified a certain kind of pulsating star, called a Cepheid variable, inside Andromeda. Cepheids brighten and dim on a schedule tied directly to their true brightness, which meant Hubble could calculate how far away one had to be to look as faint as it did. The answer put Andromeda more than 1 million light-years away, far outside the Milky Way, and overturned a debate that had run for years about whether the universe contained one galaxy or billions. That distinction between things bound by gravity and things simply carried apart by the expansion of space is the one piece of physics that everything else in this account depends on. Space itself stretches over time, a discovery that also traces back to Hubble's work in the 1920s, and that stretching carries galaxies away from one another faster the farther apart they already are. But gravity can win locally if there is enough mass close enough together, and inside the local group it wins outright. The Milky Way, Andromeda, and their smaller companions are bound tightly enough that the stretching of space between them is negligible. They orbit a shared centre of mass, the same basic physics that keeps the Moon circling Earth, just stretched out over distances 1 billion times larger and timescales 1 million times longer. The scale is easier to hold on to with a comparison. If the Milky Way's disk were shrunk down to the size of a dinner plate, about 30 centimetres across, the local group at that same scale would be a sphere roughly the size of a basketball court, with the Milky Way and Andromeda as two plates sitting near opposite ends of it, and dozens of smaller crumbs scattered in between. Nothing beyond that basketball court at this scale is gravitationally bound to the Milky Way anymore. Beyond it, the universe's expansion takes over, and the story of the Milky Way's real address moves from a single bound group to something built entirely out of motion. Even so, the local group does not drift outward in a perfectly straight line, the way pure expansion alone would carry it. When astronomers measure its motion carefully, comparing how fast it appears to be approaching or receding from thousands of other galaxies across the sky, they find a deviation, an extra pull, layered on top of the expansion, aimed in a specific direction. Something massive out there is tugging on the local group, bending its path. Finding out what that something is, and how big a structure it turns out to belong to, is most of what follows. For now, picture the Milky Way not as the center of anything, but as a single grain of sand, carried inside a slow, wide current made of thousands of other galaxies, all drifting in roughly the same direction across tens of millions of light years. Currents have destinations, or at least a direction. The nearest landmark on this one is a dense, bright knot of galaxies that has been visible to astronomers for centuries, long before anyone understood what its gravity was doing to everything around it. Beyond the edge of any single bound galaxy group, gravity does not vanish. It only stops being strong enough to hold things in fixed orbits against the stretching of space itself. What takes over instead is a looser kind of structure, one held together only as long as everything inside it happens to be moving in roughly the same direction, at roughly the same pace, relative to the overall expansion of the universe. Astronomers call these structures superclusters, and unlike a galaxy or a galaxy cluster, a supercluster is not a single object bound by its own gravity into a stable, lasting shape. It is closer to a traffic pattern than a building, a description of which way galaxies are flowing at this moment rather than a thing they are permanently attached to. Untangling that flow requires separating two kinds of motion that are mixed together in every measurement astronomers make of a distant galaxy. The first is the expansion of space itself, the Hubble flow, which carries every distant galaxy away from every other one at a rate proportional to distance, a relationship discovered in the 1920s. And confirmed many times since. A galaxy twice as far away recedes, on average twice as fast. The second is what is called peculiar velocity, the galaxy's own motion through space, caused by the gravity of whatever nearby mass is pulling on it, layered on top of the expansion like a current riding on top of a tide. Pull those two apart for enough galaxies across enough of the sky, and the pattern of peculiar velocities traces out where the mass actually is, even mass too faint or too spread out to see directly. That is exactly the technique that eventually explained the small deviation in the local group's own motion, the extra pull noted earlier that the expansion of space alone could not account for. Long before the technique existed in its modern form, astronomers had already noticed something suggestive with a much cruder tool, a simple map of where galaxies cluster most densely on the sky, and in the direction of the constellation Virgo, high overhead in the northern spring sky. That map showed an obvious concentration, a crowd of galaxies far denser than the average patch of sky nearby. It had been catalogued since the 18th century, when the French astronomer Charles Messier and his contemporaries, hunting for comets, kept running into fuzzy patches of light that refused to move against the stars the way a comet should, and listed them instead as things to avoid mistaking for one. Many of those fuzzy patches, it would later turn out, were entire galaxies, and a striking number of them sat clustered together in one small region of sky. A word of caution belongs here, because two similar-sounding terms are about to carry very different weight for the rest of this account. A galaxy cluster is a genuinely bound structure, hundreds or thousands of galaxies held together by gravity strongly enough to have settled, over billions of years, into a roughly stable system, the way stars settle into a stable orbit around a galaxy's center. A supercluster is something else again. A collection of clusters and smaller groups that share a common direction of motion, without ever having settled into one bound system, because the distances involved are too large, and the age of the universe is too short for gravity to have finished the job. The cluster in Virgo belongs to the first category. What it turns out to sit inside belongs to the second, and confusing the two is exactly the mistake that took decades to fully sort out. How much time gravity needs to finish organizing structure into a single bound clump depends entirely on scale. A star cluster of a few thousand stars can settle into a stable shape in a few tens of millions of years. A galaxy, built from hundreds of billions of stars and dark matter besides, takes closer to 1 billion years. A structure the size of a galaxy cluster, spanning millions of light years, needs several billion years, which is why even the most massive clusters observed today are still visibly assembling, still swallowing smaller groups that fall in along filaments of gas and dark matter. A structure the size of a supercluster, tens or hundreds of millions of light-years across, would need many times the current age of the universe, roughly 13.8 billion years. To ever finish collapsing into one bound object, it never will. Long before gravity could finish that job, the accelerating expansion of the universe, driven by the effect now called dark energy, will have pulled the pieces too far apart for gravity to win. That fact will matter again much later in this account. Not every patch of sky is converging on something crowded. Exactly the opposite pattern exists too. Enormous regions containing far fewer galaxies than average, sometimes called voids, where the peculiar velocities point outward instead of inward, as though the region were gently deflating rather than being pulled together. A void is not empty in any technical sense, but it can be genuinely underdense by a wide margin, and its shortfall of gravity compared to its surroundings pushes galaxies at its edges away just as surely as an overdense cluster pulls them in. Mapping both kinds of region together, the crowded ones and the emptied ones, is what eventually let astronomers draw a complete picture of the flow the local group is caught inside, rather than just the single obvious landmark in Virgo that started the search. The knot of galaxies in Virgo is the natural place to look first because it is close enough to study in detail and massive enough that its gravity is the leading suspect for the local group's extra pull. Getting a clear picture of what is actually sitting there, at the center of a structure the Milky Way has been drifting toward for billions of years, is the next step outward. At the heart of that crowded patch of sky sits the Virgo Cluster, the nearest large galaxy cluster to the local group and the first serious landmark on the outward journey. It lies roughly 54 million light-years away, more than 5 times farther than Andromeda, and it holds far more than the local group's roughly 80 members. Current catalogues list more than 1,000 galaxies, and some estimates that include the faintest dwarf members run past 2,000, packed into a region only about 15 million light-years across, a little wider than the local group but far more crowded. At its center sits a single enormous elliptical galaxy called Messier 87, or M87 for short, a galaxy built almost entirely from old red stars rather than the young blue ones that light up spiral arms, and containing something like 10 times as many stars as the Milky Way. M87 hosts a supermassive black hole with a mass of about 6.5 billion times the mass of the Sun, a black hole so large and so well positioned that in 2019 it became the first one ever directly imaged. Its shadow captured against a glowing ring of infalling gas by a global network of radio telescopes working together as the Event Horizon Telescope. A brilliant jet of particles, blasted outward from near the black hole at speeds close to the speed of light, streams for thousands of light-years from M87's center, visible even in modest telescope images as a straight blue streak cutting across the galaxy's fuzzy halo. M87 is not the most massive thing in the Virgo cluster, though. That title belongs to something far less visible, a vast reservoir of extremely hot gas, heated to tens of millions of degrees, filling the space between the galaxies rather than sitting inside any one of them. This intracluster gas, detectable mainly through the X-ray light it emits, outweighs all the stars in all the cluster's galaxies put together, and its presence is one of the clearest signs that a cluster like Virgo is a single, gravitationally bound system rather than just galaxies that happen to be nearby one another. Gas that hot can only stay put, rather than escaping into intergalactic space if it is held in place by an enormous, mostly invisible reservoir of gravitating mass, made up mostly of dark matter, matter that does not emit or absorb light but whose gravity can still be measured through its effect on everything around it. The Virgo cluster is also not one single smooth clump, but several subclumps still in the process of merging with each other, each centered on its own giant elliptical galaxy, one dominated by M87 itself, a second centered on a galaxy called M86, and a third around M49, each with its own smaller retinue of galaxies and its own pocket of hot gas, all gradually falling together under their combined gravity. Untangling these subclumps from one another is part of why early estimates of the cluster's total size and mass varied so much from one survey to the next, and why later, more careful maps of galaxy distances, rather than just positions on the sky, were needed before astronomers trusted a single figure for how far away the cluster's center actually sits. The Virgo cluster is not finished forming. Individual galaxies and smaller groups, are still falling into it along filaments of gas and dark matter that connect it to the wider cosmic web, arriving with their own gas still intact, and then, in many cases, having that gas stripped away as they plough through the hot intracluster medium at speeds of 1,000 kilometers per second or more, a process called ram pressure stripping. Galaxies caught mid-collision with the cluster's gas often show long, glowing tails trailing behind them, gas torn loose and left behind like a scarf pulled off in a strong wind, a visible record of exactly how fast and how forcefully the cluster is still gathering material even now, more than 13 billion years after the universe's earliest structures began to form. The light reaching Earth from the Virgo cluster tonight left those galaxies about 54 million years ago, long before any human being existed to see it, at a time when the continents on Earth were still shifting toward roughly their present shape, and the first primates were only beginning to appear in the fossil record. Nothing about the cluster has been static in that time. But at the scale this account is working at, 54 million years is close enough to instantaneous that the picture astronomers see is a fair snapshot of the structure as it stands today. None of this on its own explains why the local group's motion bends specifically toward Virgo rather than drifting in a straight line, shaped only by the universe's overall expansion. That answer required a separate, more painstaking kind of measurement, not simply cataloguing how many galaxies sit in the direction of Virgo, but clocking exactly how fast the space around the local group itself is moving, and in which direction. Clocking the local group's true motion meant separating, once again, the two kinds of speed folded into every measurement of a distant galaxy, the expansion of the universe, and whatever additional peculiar velocity gravity has added on top of it. For a galaxy sitting in an essentially random direction, those two speeds simply add up in the redshift astronomers measure the stretching of a galaxy's light toward longer, redder wavelengths caused by its motion away from Earth. But for galaxies lying specifically in the direction of Virgo, something did not add up cleanly. Their redshifts implied they were receding slightly slower than their distance, measured by other means entirely, said they should be. And on the opposite side of the sky, directly away from Virgo, the pattern reversed. Galaxies out there appeared to be receding slightly faster than expected. That lopsided pattern is exactly the signature gravity leaves on a flow of galaxies converging toward a massive object. Imagine every galaxy around the local group moving outward with the universe's expansion, and then imagine one especially massive cluster nearby adding its own extra pull on top, tugging every galaxy in the general area a little bit toward itself, including the local group. Galaxies between us and that cluster get an extra push toward it, reducing how fast they appear to recede. Galaxies on the far side of us from that cluster get pulled the same direction, which happens to be away from Earth, adding to their apparent recession speed. The local group itself is caught in the middle of that same tug, drifting toward Virgo at a speed of roughly 300 kilometers per second, on top of the universe's ordinary expansion, a figure astronomers refined over several decades of increasingly careful measurement starting in the 1970s. Astronomers named the effect Virgo-centric infall, and confirming it required a way to measure a galaxy's true distance that did not rely on its redshift at all, since redshift was the very thing under suspicion of being skewed. Several independent methods, refined through the 1970s and 1980s, filled that role, comparing the true brightness and apparent brightness of certain kinds of stars, or relating a spiral galaxy's rotation speed to its intrinsic luminosity. Every method that did not depend on redshift agreed with the others, and all of them confirmed the same lopsided pattern. The Virgo cluster really was pulling on its surroundings, hard enough to measurably bend the paths of galaxies tens of millions of light years away. Among the first to propose that Virgo's gravity could explain the anomaly was Gerard de Vaucouleurs, the same astronomer who would soon attempt the first full map of the structure surrounding it, working alongside the Estonian astronomer Jan Einasto, who was independently mapping similar patterns using galaxy clusters in other parts of the sky. Their proposal was controversial at first. It required accepting that a single cluster's gravity could measurably distort the expansion of the universe itself across tens of millions of light years, a claim that needed years of accumulating, independently confirmed distance measurements before most astronomers accepted it as established fact, rather than an interesting hypothesis. To put that pull in scale, the Virgo cluster's total mass, most of it in the form of dark matter rather than stars or gas, has been estimated at somewhere around 1,000 trillion times the mass of the Sun, spread across a region 15 million light-years wide. If the Sun's mass were represented by a single grain of sand, that total would fill a volume the size of a large moving truck, and every particle of it, spread across a region larger than the local group itself, contributes to the same steady tug that is quietly reshaping the trajectory of every galaxy for tens of millions of light-years around, including the one this account calls home. By the middle of the 20th century, astronomers had enough evidence in hand, the crowded map of galaxies in Virgo, and the measured pull on their own galaxy, to suspect that the local group and the Virgo cluster belonged to one much larger structure together. Turning that suspicion into an actual map, with an actual size and an actual shape, was the next problem, and the first serious attempt to solve it came from a French-born astronomer working mostly in the United States, using nothing more sophisticated than an exhaustive galaxy catalogue and a great deal of careful counting. Gerard de Vaucouleurs spent much of the 1950s and 1960s doing something almost nobody else was doing at the time, treating the distribution of nearby galaxies not as a scattered, essentially random field, but as a single connected structure worth mapping in its own right. Building on decades of galaxy catalogues, his own observations, and the work of earlier astronomers who had noticed the same crowding in Virgo, he proposed that the local group, the Virgo Cluster, and dozens of smaller groups and clusters scattered around them all belonged to one flattened, disc-shaped structure, which he called the local supercluster. It would later become known, more descriptively, as the Virgo Supercluster, since the Virgo cluster sat close to its centre and clearly dominated its gravity. De Vaucouleurs estimated the structure at roughly 110 million light-years across, and only about a tenth of that in thickness, a broad, flattened disk rather than a sphere, not unlike a colossal, thin dinner plate with the Virgo cluster near its middle and the local group out toward its edge, roughly a third of the way from the centre to the rim. That flattened shape was not an assumption. It came directly from the data. When de Vaucouleurs plotted the positions of thousands of galaxies in 3 dimensions, using whatever distance estimates were available at the time, they did not scatter evenly through space. They clumped along a broad, roughly planar sheet with much emptier regions above and below it. The method had real limits, and de Vaucouleurs was aware of most of them. Distance measurements for galaxies in the 1950s and 1960s were far cruder than they would later become, so the 3-dimensional map was really closer to an educated reconstruction stitched together from imperfect distance estimates and the reasonable assumption that galaxies which looked close together on the sky and had similar redshifts were probably close together in space as well. That assumption breaks down exactly in the situation the previous chapter described. Near a massive cluster like Virgo, redshift is not a clean stand-in for distance, because the cluster's own gravity distorts it. The map de Vaucouleurs drew was a genuine achievement and the first serious attempt at the job, but it was built on a foundation that had a known, specific flaw at its very centre. There was a second, deeper problem, one that would not become fully clear for another half-century. De Vaucouleurs had defined his supercluster by density. Draw the map, look for where galaxies are more crowded than the average, and call the crowded region a structure. But density on its own does not tell you which galaxies are actually gravitationally influenced by which mass or which direction any given galaxy's own motion is actually being bent. 2 neighbouring regions could look equally dense on a map while belonging to completely different, oppositely flowing streams of galaxies, in exactly the way 2 neighbouring valleys on either side of a mountain ridge can look similar from above while every drop of rain that falls on them runs downhill in opposite directions. A map based purely on density had no way to see that difference. Other astronomers, working through the 1970s and 1980s, found similar structures elsewhere in the sky. Crowded regions of galaxies around the Coma cluster, around the Hydra and Centaurus clusters, around Perseus and Pisces, each got its own name, its own rough size, its own place on an increasingly detailed map of the nearby universe. By the 1980s, dozens of these superclusters were catalogued this way, essentially as large-scale cousins of de Vaucouleurs' Virgo Supercluster, all defined the same way, by counting where galaxies clustered more densely than their surroundings. The overall picture that emerged, sometimes called the cosmic web, showed galaxies concentrated along broad sheets and filaments, with enormous comparatively empty voids between them, a structure confirmed again and again by larger and larger surveys, through the 1990s and 2000s. But every supercluster in that catalogue carried the same unresolved flaw as the very first one, a boundary defined by counting galaxies, not by tracing where their gravity was actually taking them. For decades, de Vaucouleurs' local supercluster, the Virgo Supercluster, remained the standard picture, a specific, roughly disc-shaped, 110 million light-year structure with a name, a shape, and a size taught in textbooks essentially unchanged. It took a different kind of measurement entirely, one built not on where galaxies sit but on which way they are actually moving, to reveal that the true structure surrounding the Virgo cluster was several times larger than de Vaucouleurs had ever proposed, and that his supercluster was not wrong, so much as it was only one piece of something bigger. Fixing that flaw meant giving up on density as the defining measurement and switching to something harder to gather but far more meaningful. The actual, three-dimensional velocity of each galaxy, split into its expansion component and its peculiar velocity, the same technique that had already revealed the local group's own pull toward Virgo. Doing this for a single galaxy or a small handful, as the Virgo-centric infall studies had done, was demanding enough. Doing it for tens of thousands of galaxies spread across hundreds of millions of light-years, in every direction, was a project that took decades, and much of that project was led by an American astronomer named R. Brent Tully, working for many years alongside French astrophysicist Hélène Courtois and other collaborators. The key tool making it possible was a relationship Tully had published in 1977, together with astronomer Richard Fisher, a spiral galaxy's rotation speed, how fast its outer stars and gas swing around its center, turns out to correlate closely with its true intrinsic brightness. Measure how fast a distant spiral galaxy is spinning, using the spread in the wavelengths of light coming from its approaching and receding edges, and the Tully-Fisher relation gives a reliable estimate of how bright that galaxy really is. Compare that true brightness to how bright it actually appears from Earth, dimmed by distance the way a lamp looks fainter the farther away it is, and the comparison yields a distance estimate that does not depend at all on redshift. Subtract the expansion predicted for that distance from the galaxy's measured redshift, and what is left over is its peculiar velocity, its own true motion through space, caused by whatever is gravitationally pulling on it. Applied one galaxy at a time, the technique is useful. Applied to tens of thousands of galaxies across a large volume of space, it does something much more powerful. It lets astronomers reconstruct an entire three-dimensional flow field, essentially a map of which way everything is moving, everywhere, all at once. And a flow field, unlike a simple density map, has a genuine physical structure that can be traced the same way a hydrologist traces where rainfall drains. Picture the whole region as a landscape of gravitational hills and valleys, invisible but real, shaped by the uneven distribution of mass, most of it dark matter, spread through space. A galaxy sitting anywhere on that landscape drifts the way water would, downhill toward the nearest low point, the deepest gravitational basin its own local terrain drains into. Two galaxies can sit reasonably close together in space and still belong to entirely different basins if a ridge of lower density runs between them, in exactly the same way that a raindrop falling a few meters to one side of a mountain ridge can end up in an entirely different ocean than a raindrop falling just the other side. This gave Tully and his collaborators a new and far more rigorous definition of a supercluster, not a region where galaxies happen to be more numerous, but a single basin of attraction, a complete gravitational catchment whose every galaxy is, on balance, flowing toward the same low point rather than toward some neighboring low point across a dividing ridge. Two regions could look equally dense in an old-style map and still belong to entirely separate basins under this new definition. Exactly the ambiguity that had haunted density-based supercluster maps since de Vaucouleurs' original attempt. Untangling the actual basin boundaries required assembling a distance and velocity catalogue for tens of thousands of galaxies, a painstaking observational campaign that took the better part of 2 decades to complete. The resulting catalogue, published in stages under the name Cosmicflows, eventually included distance and velocity measurements for more than 8,000 galaxies directly, with tens of thousands more added through related surveys, covering a volume of space roughly 1 billion light-years across. It remains one of the largest deliberate efforts ever undertaken to measure not just where galaxies are, but which way they are actually going. By the early 2010s, that catalogue was finally large and precise enough to compute a full velocity flow field for the volume of space surrounding the local group out to several 100 million light-years in every direction. Running the numbers revealed the low point the whole region was actually draining toward, and it was not simply the Virgo cluster. It was something considerably larger, extending well past the boundary de Vaucouleurs had drawn 6 decades earlier, with Virgo sitting only in one corner of it. The basin that emerged from the Cosmicflows velocity map was published in 2014 in a paper in the journal Nature by Tully Courtois and 2 more collaborators, Yehuda Hoffman and Daniel Pomereed. It stretched roughly 500 million light-years from end to end, nearly 5 times the diameter de Vaucouleurs had proposed for his Virgo Supercluster, and it contained, by the team's estimate, something like 100,000 galaxies, with a total mass equivalent to roughly 100 quadrillion suns. Every one of those galaxies, according to the flow field calculation, shares a single gravitational basin, all of them drifting, at least on balance, toward the same broad low point in the cosmic landscape. The team needed a name for it, and reached deliberately past the usual practice of naming a structure after whichever cluster happens to sit inside it. Tully worked with Nawar Napoleon, a professor of Hawaiian language, to find a term that captured the structure's true character rather than one landmark within it. They settled on Laniakea, a Hawaiian word meaning immeasurable heaven, chosen partly in honor of Polynesian navigators who once crossed the Pacific Ocean using detailed knowledge of stars and currents invisible to anyone who did not know exactly what to look for, in much the way a velocity flow field reveals a structure invisible to any map based on density alone. Under this new definition, de Vaucouleurs' Virgo Supercluster did not disappear and was not shown to be wrong. It was simply revealed to be one lobe, one arm, of a much larger basin, the piece nearest to the local group, and the one first mapped in detail because it was close enough to study with the cruder tools available in the 1950s. Laniakea, the complete basin, gathers several such lobes together. The Virgo Supercluster containing the local group, along with others named for the clusters that anchor them, including the Hydra Centaurus lobe, and several others besides, all draining toward one shared gravitational low point near the basin center. The scale is difficult to hold in mind without a comparison. If the local group, that 10 million light-year sphere the size of a basketball court in the earlier comparison, is shrunk down to the size of a single marble, Laniakea at the same scale would be a sphere more than 20 meters across, roughly the length of 2 school buses parked end to end, with tens of thousands of marbles scattered through its volume, most of them clustered along a handful of connected lobes rather than spread evenly through the whole space. That single marble, somewhere out near the edge of one lobe, is where every human being who has ever lived has spent their entire existence. Pomereed, the team's 4th author, built 3-dimensional computer visualizations of the entire flow field, rendering each galaxy's measured velocity as an arrow pointing toward its local downhill direction, and it was those visualizations, more than the raw numbers, that made the shape of Laniakea immediately legible, a webbed, asymmetric basin with several connected valleys, rather than the flattened disk de Vaucouleurs had once imagined, its true 3-dimensional shape closer to a loosely connected cluster of watersheds than to any simple geometric figure. Laniakea's low point, the deepest part of the basin toward which the whole structure drains, is not simply the Virgo cluster, and locating it precisely required going back to a gravitational anomaly astronomers had already been arguing about for years, hidden almost directly behind the disk of the Milky Way itself. That low point sits in a direction astronomers call the Zone of Avoidance, the band of sky where the Milky Way's own disk, thick with gas, dust and crowded foreground stars, blocks a clear view of almost everything beyond it. Optical telescopes are nearly useless looking through that band. The dust simply absorbs too much light. Radio and infrared observations, which pass through dust far more easily, eventually revealed what optical surveys had missed for decades, an unusually massive concentration of galaxies sitting almost directly behind the Milky Way's disk at a distance of roughly 150 million light-years, a region astronomers had already nicknamed the Great Attractor in the 1980s, well before anyone understood exactly what it was pulling on or how large a structure it anchored. Finding Laniakea's actual outer edge, once the locations of its gravitational floor was known, meant tracing the flow field outward from that low point in every direction until the flow itself stopped converging and started diverging instead, or started converging towards some other, competing low point belonging to a neighboring basin. Mathematically, that transition happens at what is called a saddle point, a location where the gravitational landscape curves upward in one direction and downward in another, the exact three-dimensional equivalent of a mountain pass, the lowest point along a ridge but still higher than the valley floors on either side of it. Every saddle point the team identified around Laniakea's perimeter marked a genuine boundary, a place where a galaxy's fate, whether it belongs to Laniakea or to some neighbouring basin, could tip either way depending on which side of the ridge it happened to sit on. That boundary is the invisible watershed line running around Laniakea's edge, drawn not through any density of galaxies, and not through any wall of matter a spacecraft could ever cross and notice, but purely through the direction of motion on either side of it. Stand on one side of that line, gravitationally speaking, and the flow of galaxies around you drains toward Laniakea's centre, tens of millions of light years away. Stand on the other side, sometimes only a modest distance away in ordinary terms, and the flow drains toward an entirely different low point belonging to a different basin altogether. Nothing about the galaxies themselves changes at that line, only the direction they are, on balance, headed. The precision of that boundary is not perfect, and the original 2014 paper was careful to say so. Velocity measurements carry real uncertainty, especially for the more distant galaxies used to trace the flow field's outer reaches, and later surveys with denser galaxy sampling have refined the exact shape of Laniakea's edge more than once since 2014, occasionally moving a given galaxy from one side of the boundary to the other as better data arrived. The broad picture, a 500 million light-year basin centered near the Great Attractor with the Virgo Supercluster as one lobe, has held up well against those refinements. The precise galaxy-by-galaxy edge remains a live, ongoing measurement rather than a settled line on a final map. The cluster anchoring the Great Attractor is now generally identified as the Norma cluster, catalogued formally as Abell 38627, sitting almost exactly in the direction of the Great Attractor's calculated position and at roughly the right distance, though its own mass alone still falls short of fully explaining the size of the pull first measured in the 1980s, a gap that pointed astronomers toward yet another, larger structure lying just beyond it. The Great Attractor itself, sitting at Laniakea's gravitational floor, turned out to be anchored by yet another galaxy cluster, one that had been hidden behind the Milky Way's dust for just as long as the attractor it belonged to. And even that cluster, once its own mass and motion were fully measured, was not the final word on what was pulling on the local group. Something considerably larger, and considerably farther away, appears to be tugging on Laniakea's own gravitational floor. That larger structure is the Shapley Supercluster, a concentration of galaxy clusters roughly 650 million light-years away, on almost the same general line of sight as the Great Attractor, but nearly 4 times farther out, making it, by most estimates, the single densest concentration of galaxy clusters in the observable universe within 1 billion light-years of Earth. Named for the American astronomer Harlow Shapley, who first catalogued an unusual density of clusters in that region in the 1930s, long before anyone understood its true scale, the Shapley Supercluster is massive enough that some researchers have proposed it exerts a measurable gravitational pull on Laniakea itself, tugging the entire basin, Great Attractor and all, gently in its direction. That proposal remains an active area of research rather than settled fact. The evidence draws on the same kind of peculiar velocity measurements used to map Laniakea, extended out to much greater distances where the signal is fainter and the uncertainties are larger, so astronomers describe the Shapley Supercluster's influence with real caution. It is a plausible and currently favoured explanation for part of the local group's total motion, not a proven one. What is measured with much higher confidence is the local group's total peculiar velocity relative to the cosmic microwave background, the faint, ancient glow left over from the early universe that fills all of space and provides the closest thing cosmology has to an absolute reference frame. That measurement puts the local group's total motion, expansion aside, at roughly 620 kilometers every second, a speed too large to be explained by the Great Attractor and the Virgo Cluster's pull alone. Explaining the shortfall took a second discovery, announced in 2017 by a team that included some of the same researchers behind the original Laniakea map, not another attractor pulling from the front, but a void pushing from behind. They called it the dipole repeller, an unusually empty region of space roughly opposite the Shapley Supercluster's direction on the sky, containing far fewer galaxies and far less mass than its surroundings. A region that empty exerts an effect exactly like the voids described earlier. Rather than pulling galaxies toward it, its shortfall of gravity, compared to the denser regions around it, effectively pushes everything at its edges away, adding its own contribution to the local group's total measured speed. Combining the pull from Shapley's direction with the push from the dipole repeller's direction accounted for the local group's total observed motion far better than either effect could on its own. The picture that emerges is one of nested influence, rather than a single simple answer to the question of what is pulling on the Milky Way. The Virgo Cluster pulls. The Great Attractor, anchored by the Norma Cluster, pulls harder from farther away, and Virgo's own pull turns out to be only one contribution folded into that larger tug. The Shapley Supercluster may pull harder still, from farther away again, its influence still being refined. And the dipole repeller, an absence of mass rather than a presence of it, pushes from the opposite direction, adding its own share. Each layer explains a portion of the total motion. None of them, on its own, explains all of it, and every one of them was found by patiently subtracting the layer before it from the same underlying measurement. Astronomers reached these conclusions only by refusing to settle for the first explanation that fit the data reasonably well. The Virgocentric infall alone looked, for a while, like a complete answer. The Great Attractor once found looked complete in turn. Each time a residual, a small leftover discrepancy between prediction and measurement, pointed towards something farther out still, a pattern that has repeated at every scale examined in this account so far, and shows no obvious sign of stopping at Shapley either. None of these structures, whatever their final measured sizes turn out to be, will last in any of the ways an object like a planet or even a galaxy lasts. That is not a limitation of the measurement, it is a basic consequence of the physics governing the universe on the largest scales, and it means that Laniakea, the entire half-billion light-year basin the local group calls home, is best understood not as a place with a permanent size, but as a single frame in a very slow, very large-scale ongoing motion. The reason Laniakea will not last comes down to a single competition, playing out at every scale in the universe, between gravity's pull inward and the universe's own expansion pulling everything apart. Inside a bound structure like the local group or the Virgo Cluster, gravity has already won that competition decisively, and will keep winning for as long as those structures exist. The mass is concentrated enough and close enough together that the expansion of space between individual members is effectively negligible. A structure the size of Laniakea sits on the opposite side of that competition. Its member galaxies are pulled toward the shared basin, but not strongly enough, and not for long enough, to ever fully overcome the expansion trying to carry them apart. Since the late 1990s, that competition has had an extra factor working against gravity's side. Observations of distant exploding stars called Type Ia supernovae, useful because their true brightness can be calculated reliably, revealed that the universe's expansion is not merely continuing, it is accelerating, speeding up over cosmic time rather than gradually slowing down the way gravity alone would predict. The cause is attributed to dark energy, a term covering whatever is responsible for that acceleration, currently estimated to make up close to 70% of the total energy content of the universe, dwarfing the roughly 25% made up of dark matter and the roughly 5% made up of the ordinary matter that stars, planets, and people are built from. Astronomers do not yet have a settled physical explanation for what dark energy actually is at a fundamental level, only strong, repeated observational evidence that its effect is real. For a structure as loosely bound as Laniakea, an accelerating expansion is decisive. Current models predict that over the coming tens of billions of years, the basin's outer lobes will drift farther and farther from its gravitational center, their peculiar velocities overwhelmed by ever faster cosmic expansion, until eventually the connections that currently define Laniakea as a single flow field structure stop existing in any meaningful sense at all. The Virgo Supercluster's lobe, the local group's home corner of the larger basin, will likely still hold together in some rough sense for far longer, since its own internal gravity is somewhat stronger than the basin's overall pull. But Laniakea as a whole, the complete 500 million light-year structure mapped in 2014, is a snapshot of a moment, not a description of anything that will persist. A useful way to hold that timescale is against the universe's own age so far. The universe has existed for about 13.8 billion years. The most optimistic models for how long it would take gravity, to fully assemble a structure the size of Laniakea into one genuinely bound object. Put that job at somewhere well over 100 billion years, roughly 7 or 8 times the universe's current age, and that estimate assumes an expansion that eventually slows down. With dark energy instead accelerating the expansion, that assembly will never finish. If the universe's entire history to date were compressed into a single 24-hour day, Laniakea would be a structure identified only in the last fraction of a second before midnight, already unravelling even as it was first mapped. None of this makes the local group itself any less secure. The gravitational bond holding the Milky Way and Andromeda together, and even the somewhat looser bond holding the whole local group and the wider Virgo Cluster region together on a timescale of billions rather than tens of billions of years, is strong enough that dark energy's accelerating pull will not visibly loosen it within any time frame relevant to a description of the present. It is only at the very largest scales, the scale of a Laniakea rather than a local group, that the expansion's advantage becomes decisive within a time frame astronomers actually model with confidence. Even structures that will not last, though, still shape everything that lives inside them while they exist, and Laniakea's shape did not appear randomly. It traces directly back to the earliest moments of the universe, when tiny variations in density, present from almost the very beginning, were stretched, amplified by gravity, and eventually grew into the entire web of filaments, sheets, and voids the local group now finds itself woven into. Those earliest variations trace back to a period less than a billionth of a second after the Big Bang, when the entire observable universe was compressed into a volume far smaller than a single atom, and quantum fluctuations, the same fundamental randomness that governs particles at the smallest scales, produced tiny differences in density from one point to the next, differences of only about 1 part in 100,000, relative to the average, imprinted permanently into the fabric of space during an extremely brief period of accelerated expansion called cosmic inflation. Those tiny differences did not stay tiny. Regions that started out even slightly denser than average pulled in extra matter through gravity, becoming denser still, while regions that started out even slightly less dense than average lost matter to their denser neighbours, becoming emptier still, a runaway process that continued for billions of years as the universe expanded and cooled. The clearest surviving record of the original, unamplified pattern is the cosmic microwave background, the same ancient light mentioned earlier as cosmology's reference frame, a faint glow filling the entire sky, released when the universe was only about 380,000 years old, and had cooled enough for light to travel freely for the first time. Tiny temperature variations in that glow, mapped in exquisite detail by space telescopes over the past few decades, match the seeds that grew into every galaxy, cluster, and supercluster observed today, including Laniakea. The result, after more than 13 billion years of that amplification, is the structure cosmologists call the cosmic web. Galaxies concentrated along long, thin filaments and broader sheets, meeting at dense nodes where clusters like Virgo or the Norma cluster sit, with enormous, comparatively empty voids filling the spaces between the filaments, some of those voids hundreds of millions of light-years across in their own right. Laniakea occupies one node and filament neighbourhood of that web. Others lie beyond its boundary in every direction. The Perseus-Pisces Supercluster, another dense filament of clusters roughly 250 million light-years away. The Coma Supercluster, farther out still, and beyond all of them, at scales approaching 1 billion light-years, enormous, only partly mapped concentrations that some researchers have proposed, calling superclusters of superclusters, structures so large that classifying them with any confidence remains an open problem. Confirming that this same filament and void pattern holds true across the observable universe, not just in the relatively nearby volume Cosmicflows mapped, required large redshift surveys recording the distance and position of hundreds of thousands, and eventually millions, of galaxies across enormous stretches of sky, a project that began in earnest in the 1980s and has continued, with ever larger telescopes and ever more automated instruments, into the present day. Every one of those surveys has found the same basic pattern, never a uniform scattering of galaxies, and never a random one either, but always the same filaments, sheets and voids, at every scale large enough to check, all the way out to the edge of what current telescopes can usefully measure. What makes this pattern remarkable is not just its scale but its consistency. A supercluster mapped near the Norma cluster and one mapped near Perseus and Pisces formed from the same physics. The same tiny seed fluctuations amplified by the same gravity over the same span of cosmic time, and yet each one carries its own distinct shape, its own particular lobes and voids. The way two rivers shaped by the same rainfall and the same geology still carve entirely different courses across a landscape. No two superclusters, so far as current surveys can tell, are identical. Laniakea, then, is neither an isolated curiosity nor the largest thing that exists. It is one recognizable knot in a much larger, still only partly mapped web, distinguished mainly by the fact that it happens to be the one knot the Milky Way itself is woven into. Which brings the account back to the question it opened with. After everything measured, mapped, renamed, and refined across 60 years of astronomy, what is the honest answer to how big the Virgo Supercluster actually is? The honest answer has two parts, and both of them are true at the same time without contradicting each other. If the question means the specific structure Gerard de Vaucouleurs mapped in the 1950s and 1960s, the flattened disk of galaxies centered on the Virgo cluster and containing the local group, then the answer has not changed. Roughly 110 million light-years across, home to the Milky Way, Andromeda, and everything gravitationally entangled with the Virgo cluster's immediate surroundings. That structure is real. Its size was never wrong. If the question means the complete gravitational basin that structure actually belongs to, the answer is Laniakea, roughly 500 million light-years across, containing on the order of 100,000 galaxies and a total mass near 100 quadrillion suns, with the old Virgo Supercluster as one lobe among several, anchored not primarily by Virgo but by the Great Attractor and the Norma cluster hidden behind the Milky Way's own disk, itself possibly answering to the still larger pull of the Shapley Supercluster, hundreds of millions of light-years farther out, and pushed from the opposite direction by the emptiness of the dipole repeller. Both numbers describe something true. What changed between them was not the universe, but the question being asked, and the tool being used to answer it. A map built from where galaxies sit produces one honest answer. A map built from which way galaxies are actually moving produces a different, larger and more complete one, because motion, not position, is what actually defines which galaxies share a common gravitational fate. Every structure this account has traced, from the bound orbit of Andromeda around the Milky Way, to the crowded knot of galaxies in Virgo, to the vast half-billion light-year basin draining toward the Great Attractor, is really the same underlying story told at a larger scale each time. Gravity organizing matter into structure, faster at small scales and slower at large ones, always racing against an expansion that never stops. The Milky Way, that single grain of sand carried inside a slow current of galaxies, has not stopped moving since the very first chapter of this account. It is still drifting, at more than 600 kilometers every second once, every layer of pull and push is added together, through the local group, through the Virgo Supercluster's lobe, through Laniakea's basin, toward a gravitational floor it will never actually reach, because the expansion of the universe is carrying that floor's surroundings apart faster than gravity alone could ever close the gap. The basin itself, the vast gravitational valley the local group has spent its entire existence sliding gently toward, has no wall, no edge marked by a difference in what is actually there. Its boundary is the watershed line described earlier, a place where the same kind of matter, arranged in the same kind of filaments and clusters, simply happens to be flowing in a different direction on one side than on the other. Laniakea's true size, in the end, is a description of a current, not a fence, and currents, unlike fences, are always in the process of shifting. None of this stops being true simply because the largest structures involved will not last in any permanent sense. The local group's gravitational binding to Andromeda, the Virgo cluster's grip on its own hot gas and hundreds of galaxies, even the much looser basin defined by Laniakea are all real, physically meaningful facts about the universe at this particular moment in its 13.8 billion year history, whatever becomes of them across the tens of billions of years still to come. A photograph does not stop being true just because the person in it eventually changes. Laniakea is the universe's photograph of this one region of space, taken at this one moment, using motion instead of light as its film. Somewhere within that current, on a grain of sand orbiting an ordinary star on the outskirts of an ordinary galaxy, it is possible to work all of this out using nothing more than starlight, patience, and several decades of increasingly careful measurement. That, more than any single number attached to Laniakea or the Virgo Supercluster, may be the more remarkable fact. Not how large the structure surrounding us turns out to be, but that creatures small enough to fit inside a single grain of that structure ever managed to map its shape at all. Every structure in this account, from a single spinning galaxy to a basin 500 million light-years wide, is an answer to the same question asked at a different scale. How far does gravity's grip actually reach, and in which direction is everything, on balance, headed? The Milky Way's true address turns out not to be a fixed location so much as a place inside a current drifting through the local group, through the Virgo Supercluster's lobe, through the whole of Laniakea, toward a gravitational floor the expansion of the universe will never let it reach. The Virgo Supercluster was never a wrong answer. It was simply the first, smaller answer available with the tools of the 1950s, and Laniakea is the larger one available with the tools of today. Neither is likely to be the final word. Future surveys, mapping the velocities of galaxies farther out and with greater precision, may well reveal that Laniakea itself is only one lobe of something even larger, its own watershed line eventually redrawn the way de Vaucouleurs line once was. What will not change is the underlying picture. A universe built from gravity pulling matter together at every scale it can, for as long as an ever faster expansion allows it to keep winning, and a small curious species on one grain of sand within it, patient enough to measure the difference.